Oh, and on the yeah, SAC's Instagram has it. Yeah, great. Yeah, check SAC's Instagram. They have it on there too. Okay. All right. So properties of matter and measurements. So, all right, like I said, the first 2 weeks should be review. Now, those of you who just had this class in summer, you're going to be like, oh, I know this. A lot of us are like, I mean, I kind of remember this, right? So I'm going to go over some of this quite quickly, and the other, I'm going to try and make sure that I go slowly. If I ever go too fast, just use the little buttons. Does everybody know where those little buttons are? They're in reactions. Maybe you should practice with those. One has like a slow down, one has like a speed up, right? It's kind of like the raise hand function. I talk fast, I try to talk slow, right? Yeah, I see some of your reactions on there. Yeah, there's like a bunch of all these different reactions you can do. Okay, so chemistry. What is chemistry? The study of matter and the changes that it undergoes. And what is matter? Again, matter is anything that occupies space and has mass. So a substance or a pure substance, this is just a form of matter that has a definite composition and distinct properties. Sorry, trying to look at the chat as I do this. Okay, so for example, a pure substance would be like water, gold, sugar. So we talked a lot about this at the beginning of Chem 209. Your Chem 101 and your book is going to go into more detail on these. These are pretty the basics, so I'm kind of just going to go through these quite quickly. Now, a mixture is a combination of two or more pure substances, and they retain their distinct identities. And we have two different types of mixtures. So we have homogeneous mixtures. This has the same composition throughout, like soft drinks, things like that. And then heterogeneous mixtures, and these are not the same composition. And so I always think of like a heterogeneous mixture as like a chocolate chip cookie, right? Where you can see that there's obvious differences. And a homogeneous mixture, that would be like Gatorade or Powerade, right? It looks the same. You take a sample from the top, the sample from the bottom, it looks exactly the same. So those are two different types of mixtures. And remember, these are also called solutions. I have horrible handwriting. I'll try to be neat. So homogeneous mixtures are also called solutions. So these two mean the same exact thing. Okay, now when we separate mixtures, we can separate them into this pure components. We can either use what is called distillation, which we'll talk about a little bit. So distillation separates things based on their boiling points. And so what it does is you have something like, let's say you have two things here. These are two different things, and you heat them up. And one of them, let's say, boils at like 30 degrees Celsius. So it's going to evaporate faster. And then this is a condensing tube. And this actually, if you get to organic, you'll use one of these. There's water that goes around here. And then so what happens is it's a gas, and then it gets colder, turns back into a liquid, and then you can collect the pure mixture over here. And then I can't draw at all, by the way. That's supposed to be a flask. And then what happens is you remove that flask. And then let's say the next one boils at 100 degrees Celsius. And so then this one will turn into a gas. When it gets to this, it'll turn back into a liquid. And then you'll have another mixture. So you'll have one that has one of your mixtures, and another one that has one pure substance here, and then another pure substance here. So distillation separates things based on boiling points. Right? It has to have very different boiling points. And again, you'll read more about this in your lecture. Pretty simple on these because, like I said, we did this in 209 already. Filtration, we're actually going to be doing that one in lab. Think of coffee, right? How do you get the coffee grounds with coffee? You use a filter. Filtration. Chromatography, unfortunately, we don't get to do that one. So this one actually separates it based on its polarity, which we'll talk about if you didn't do it in Chem 209. But these are different ways you can separate mixtures, either homogeneous mixtures or heterogeneous mixtures. Okay, so the difference between an element and a compound. So an element is from periodic table of the elements, right? It cannot be separated into simpler substance by chemical means. So you can't break down elements, right? Remember, our elements are protons, neutrons, and electrons. A compound is more than one element chemically combined. So a compound is more than one element chemically combined, and you can separate them based on chemical means. So for example, water is a compound, right? Compound has two or more elements. Like if you boil water, you just have water liquid goes to water gas, right? But if you run an electric current through water, then you can separate it, right? But that's the only way you can separate water. So it can be separated by chemical means. Like for example, has anybody tried putting like a marshmallow in the microwave? Don't do that, right? This is like sugar in the marshmallow will actually break up and it turns black and smells awful. That's you separating the glucose. It's actually not glucose, but it's a different form of sugar by chemical means. Okay, so let's review. And again, we spent like an hour on this in intro chem. We're only spent a few minutes here. Okay, so matter, remember, anything that takes up space and has mass. So for example, like what's not matter, think like light doesn't have mass, right? Or space, fire, but most things are matter. And the chemistry is a study of matter, meaning anything that has mass or takes up space, right? And then we can break it down into mixtures, and we have homogeneous and heterogeneous mixtures, and then pure substances. And our pure substances are elements and compounds, right? So that's pretty much how we break down matter. And again, you'll read more about this one in your book, but we covered this quite thoroughly in Chem 209 or your intro chem class. Okay, so another thing we've done, we need to make sure we know how we go from one form of matter to another. So we're pretty good with melting, right? Melting a solid to a liquid, pretty good with that. We got that, solid to a liquid, good with this. Freezing, opposite, right? Freezing, liquid to a solid. Condensation, think when you take a shower and right on the mirror, right? The water molecules condense on the mirror. Water goes from a gas to a liquid. Vaporization is exactly the opposite, a liquid to a gas. These two are the ones we forget or we don't know or we never learn because we don't really see these as much. So sublimation, think of like dry ice, right? So dry ice goes from a solid straight to a gas. So dry ice is an example of sublimation if you've seen it. Deposition is straight from a gas to a solid. Now in California, we don't really see this one very often. This would be like if you had frost on a windshield, that would be deposition. If people are like, I've never seen frost on a windshield. Okay, sometimes when it gets really, 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 really cold in winter, like really cold, and you look at like a soccer field in the morning and there's like the grass is all white, that's deposition. It's the water molecules in the air go straight to solid. And that solid is frozen water molecules, right? That's deposition. We just don't really see a lot of it in Southern California. Okay, our next thing, physical or chemical changes. So a physical change does not alter the composition or the identity of the substance. It's the molecules are in the same order at the beginning and the end. For example, when ice melts, we have ice, which is just solid water, to ice, water. It's still H2O, right? Or sugar when it dissolves. It's a solid, but then it dissolves, and now it's a liquid. But it's still, these atoms are still in the exact same order. The order of the atoms has not changed in a physical change. In a chemical change, the order of the atoms have changed. We've made something new. So a chemical change is like a chemical reaction, right? So if you have hydrogen burns in air to form water. Now, those of you who took Chem 209, remember that experiment you had when you had to put the splint in and it made this pop and it like scared you? That was this reaction, right? So you had H2 and O2 and it made water. These are in different order than this, right? So a chemical change, the molecules have rearranged. The products are no longer in the same order as the reactants. Physical change, same thing. Really, we've just changed a state. All right, now, extensive and intensive properties, right? You're going to see a bunch of these on Chem 101, and I put a bunch of these on Chem 101 because these two seem to be very difficult for us to keep in our brains. So an extensive property depends on how much matter is being considered. So how much matter there is, like mass. And think of like, well, it's summer, like Hershey's chocolate. One piece of Hershey's chocolate or the whole bar, that's an extensive property. That matters, right? They're very different. Length, volume, those are all extensive properties. It depends on the amount of matter versus intensive property doesn't depend on the amount, like the density, the temperature, or the color, right? Think of like Hershey's chocolate bar, right? If you have a piece of Hershey's chocolate or a bar, it's the same color. If you taste a piece of Hershey's chocolate or one piece versus the bar, it's the same taste, right? The density of it's the same. So intensive properties are the same no matter if you have a little bit or a lot. Extensive properties vary on how much you have, right? The mass of one square of Hershey's is much different than the mass of a whole bar of Hershey's. Like the length of a square is different than the length of a bar. The volume of a square is different than the volume of a bar, right? So extensive depends on how much. Intensive does not matter how much you have. Okay, now the SI units. So we call this International System of Units. It's called SI units. We're pretty good with these, like length, meter, mass, kilogram. Oh, this one, mass. A lot of times people think that the SI unit is a gram, but the SI unit for mass is actually a kilogram. Time is seconds. We don't use this one. Temperature, Kelvin, mole. We don't use this one either. Just to remind you, the abbreviation for mole is MOL. So MOLE is the same as MOL. Okay, so now to these metric conversions. Yep, you need to know these metric conversions. Okay, so, and you can remember these metric conversions however you want. Some people like to remember them without the negative exponents, with negative exponents. I don't care which one you use as long as you know them. They're actually not as difficult as you think. So saying that, let me show you why. I want you to notice this here. See how this goes 3, 6, 9, 12? Look here, 3, 6, 9, 12. They go by threes. Now you already know some of these because they're things we've learned. Centi, think there's 100 cents in a dollar. 100 is the same thing, right? 100, that's 10 to the 2, right? Which other one do you know? Well, nano sounds like 9. Nano sounds like 9. So if nano is 9, all you need to do is remember micro, which is 6. Milli, we should be pretty good with this one. We use milliliters and milligrams a lot, right? So milli is 1,000, deci is a 10. Kilo, we should be good with this one. We use this one a lot. Mega is 6, giga is 9, tera is 12. Yep, you kind of need to know these metric conversions. So you're going to use a lot of them in Chem 101, so it should help you, but you definitely do need to know the metric conversions. And no, you don't get a note card, you just have to know these. Okay, so volume. So volume, we use milliliters or liters or meters cubed. There is a conversion that you need to remember for volume, and it is this one. This conversion, 1 milliliter equals 1 centimeter cubed, is really the only way we can go from a volume, like a liter, right, to like a centimeter, which is like a measurement, right, like a length measurement. So this is going to help us go from milliliters to centimeters cubed. And I'm actually going to go through a couple of those questions today because people have actually sent those. Okay, density. So density is mass over volume. And just like I've shown you before, probably if you've taken this class, you don't even need to know this because you can just use unit conversions to find your density. So for example, a piece of platinum metal with a density of 21.5 grams per centimeter cubed has a volume of 4.49 centimeters cubed. What's its mass? Okay, so you can do this 2 different ways. And by the way, I'm not sure what professors you've had before. As long as I can follow your work, I'm pretty impartial on how you solve the problem. I just want to make sure that I can follow your work. So if you want to, you can see density is this. So you could have your density here. And it has a volume and you want to know mass. So you could do this. Sure, you could. But you know what's easier? Unit conversions. Right? So for unit conversions, we look at the 2 units we have. We have grams per centimeter cubed and centimeters cubed, right? So, and those of you who have not heard this before are going to hear this 1,000 times. If you have a choice between starting with something that has 1 unit or 2 units, always start with 1 unit, right? So that means I have 2 choices here. I can either start with this one that has 2 units or 1 unit. I choose 1 unit. 4.49 centimeters cubed. And now this 21.5, so I'm just going to put this here so it's in one piece. This number means the same as this. 21.5 grams per centimeter cubed, or centimeter cubed over 21.5 grams. This is the same as this, is the same as this. They are all exactly the same. We just need to decide which one we're going to use. And some people don't like it without a number. That's fine. Put a 1 there. That makes you happier. Put a 1 there. We just need to figure out which one we're going to use. Well, since centimeters cubed is here, whatever we want to get rid of has to go on the bottom. So I'm going to look for the one that has centimeters cubed on the bottom. This one has centimeters cubed on the bottom. So I have 1 centimeter cubed, and on top, 21.5 grams. Units crossed. We wanted mass. Look at that. We've got mass, right? So unit conversions, they just work really well, right? So you're going to see we are going to do so many unit conversions, right? And so when we do this, my calculator says 96.535 grams. We're going to talk about sig figs in a minute, but we all remember these. This says 3 sig figs, draw my line, 96.5 grams. All right, so again, could you have done it this way? Absolutely. That's totally fine. Could you have done it this way? Absolutely. Whichever way works with your brain is fine with me. Okay, so I always try to have a nice, neat one. By the way, here's if you did it the other way, you end up doing the exact same thing in your calculator and you end up with the same answer. Like no matter what, same answer. All right, so we're going to do a lot with density. You do a lot in Chem 101. All right, the next thing I want to talk about quickly is temperature. Here's what we use in the United States and like one European country. Here's what the rest of the world uses. This is what we're using, science. We're going to use Kelvin. So really, the only conversion that you need to know is this one. Is Celsius to Kelvin, Kelvin to Celsius. Yes, there is Fahrenheit to Celsius. Oops, Fahrenheit to Celsius. I might ask you that on your first quiz, but besides that, the world doesn't use Fahrenheit, so I'm not really going to ask you this. But here's the formula for Fahrenheit. There's a couple of different ways you could do this. You could put it in the fraction form or in the decimal form also. If I asked you a question that went from Fahrenheit to Celsius, I would give you this. You do not need to know this, right? It's just so rarely used. We won't. This you do need to know. I would give you this formula. Okay. And the reason we use Kelvin is because there's no negatives in it. So if you look here in Kelvin, see how, like if we go down here, they have like negative Kelvin. Kelvin only has positives, which when we get to our gas laws, that's why we use it, because there's no negatives. Okay, so converting Fahrenheit to Celsius, again, you might have to do this once. So if you have Fahrenheit, all you do is you plug it in. So what I've done here, this is what I do. I tell people this equation right here. So I always tell people this, I'll give you these equations, right? Both of them. This one goes from, right? This one goes from Celsius, Fahrenheit, and this one goes from Fahrenheit to Celsius. I'm not concerned that you can rearrange and do this math because this is math, not chemistry, but you should be able to plug it in and get the correct answer. So in this case, and by the way, if you want to write these two down or just put a box around these so you can use them when you're doing your Chem 101, you should do that. But again, it's in your lecture notes. So this one is Fahrenheit to Celsius. So you would just plug in this here into your Fahrenheit and then just plug it in, subtract 32, multiply by 5/9, and you get 78.3. But again, I would not expect you to know these. These would be given on any quiz or exam if you had to go from Fahrenheit to Celsius. You don't need to memorize those. You do need to know 273.15. All right. A couple more things to do, scientific notation. So again, why do we use scientific notation? Because nobody can count all these zeros and get it correct, right? So that's why we use scientific notation for really giant numbers or really tiny numbers. And so pretty much all of us should be okay with scientific notation. Remember, this number in the front needs to be between 1 and 10, meaning 1, 2, 3, 4, 5, 6, 7, 8, or 9. The exponent is just the number of times we moved the decimal. If the exponent is negative, it just means this number was less than 1, right? So this number is less than 1, has a negative exponent. If the exponent is positive, it just means the number is greater than 1. So the exponent is just the number of times you moved your 0, positive if it's bigger than 1, negative if it's less than 1. Some people like to memorize, oh, if you move it from the left, from the right, oh, let's try not to memorize things, right? Let's just remember positive greater than 1, negative less than 1. And again, you'll be practicing that a lot in your classes. Okay, now significant figures. I use significant figures a little bit differently. I only have 2 rules. Your book has like a bunch of rules, and if you took intro chem from someone else, you probably learned trailing zeros, all these different zeros. I found a way that works a little bit better, I think. You just need to know where the Pacific Ocean is and the Atlantic Ocean is. So if the decimal point is present meaning Pacific, or absent meaning Atlantic. So if the decimal point is present, you start from the Pacific Ocean side and you count all the numbers, including zeros, beginning with the first non-zero number. And we'll go over this in just a second. If the decimal place is absent, meaning Atlantic side, you start from the right, or the Atlantic side, and you count all the numbers, including zeros, beginning with the first non-zero number. Okay, so let's practice this. This is it. Those are the only 2 rules: present, absent, Pacific, Atlantic. So for example, how many sig figs are in this number? So we can see the decimal point is present. So since it's present, we are going to start from the Pacific side, starting with the first non-zero number. Our first number is a 0, so it doesn't count. Second number is a 0, so it doesn't count. Third number is a 0, so it doesn't count. Our third number here, this is a number, so we count it. Once you start counting, you don't stop. So 1, 2, 3, 3 sig figs. So again, the decimal point is present. Start from the Pacific side, and you start counting with the first non-zero number. It says 3 sig figs. Let's try one with the decimal point absent. So 4,600, there's no decimal point here. So the decimal point is absent. So we start counting absent Atlantic. Again, we start with the first non-zero number. Well, that's a 0, doesn't count. That's a 0, doesn't count. 1, 2. So this has 2 sig figs. So now, this is sig figs, right? There's only 2 rules: present, Pacific, absent, Atlantic. All right, so we're gonna do this example real quick. If you could just like type in the chat your answers, we'll just do these really quickly. How many sig figs are in this measurement? Yeah, that one's really easy, right? You don't need to know any rules for that one. Okay, how about the next one? Yeah, not so bad either, right? Pretty good with this one, 4. Okay, now we're gonna actually have our rules this time. How many sig figs in this one? Yeah, I see a lot of them, right? So if we look at this again, this time we actually have to think, right? The decimal place is present. So we start counting from the Pacific side, starting with the first non-zero number. Doesn't count, doesn't count. 1, 2, 3 sig figs. All right. Oh, how about this one? All right, I see a lot of people got this in general chem, right? Or in intro chem. For this one, right? If you have scientific notation, this is always just significant. So I always tell people just ignore this when you're doing sig figs. Pretend it's not there, right? So it's 2 sig figs. All right. How about our last one? Right, so for this one, the decimal place is absent. So we start counting from the Atlantic side, starting with the first non-zero number. Well, this is 0, so it doesn't count. 1, 2, this has 2 sig figs, right? And so there's a question for this one, right? How do you know this is 2 sig figs? So when you have something in scientific notation, the number before the X, everything is significant. So some of you have a really cool button in your computer, in your calculator that turns everything to scientific notation. Anything when you have scientific notation, the number before the X, these are all significant. So if this was like, for example, 6.40, that would have 3 sig figs. So when you're in scientific notation, when you're talking about significant figures, ignore this last piece. Always ignore the last piece with that one.